Hi everyone. We're going to talk about one-dimensional problems, and I have to say that there exist many physical phenomena whose motion is one-dimensional, and we already have a tool to study this kind of problems in one dimension. Uh, that is the Schrödinger equation. But here we suppose that Vx does not depend on time. Uh, Due to this property that Bx does not depend on time, the whole Hamiltonian will not depend on time, and we can separate the wave function in two pieces. This is the spatial, the spatial piece, and we can write the Schrödinger equation in this way. The other part, the full wave function is this, and we will write this when we finally have a result. These states are called stationary states due the uh, probability density does not depend of time. This is the same as write integral of dx is the same as write this. Yes, due to this property, because the energy is just a phase, and we are taking the complex conjugate and multiplying them. Hence, this is the same, and the probability density will not depend of time. This is why this is called an stationary state. Okay. Okay, we must distinguish several cases according to the form that Vx acquires and where E is located. By this we means E could be above Bx over all the x that belongs to the reals, and or it could be above Bx just in a region, a finite region that is plotted here. Now, another interesting case could be the one that or where E is just above Bx in this finite region. This case gives rise to the so-called bound states, which are discrete. Let's start by the step potential problem, where E is above Bx, or at least we will consider that case for now. So E is greater than B sub 0. Okay? We can have two cases. One, the case where x is less than 0 and x is greater than 0. Okay? If we consider the case where x is less than 0, we could see that the Schrödinger equation, or at least, let's start first with the classical notion of this problem. If we consider a particle which is moving with an energy E that is greater than V sub 0, this is equivalent to a particle that hits a wall and broke it and pass without problem, but with less momentum. Okay, the momentum will seems reduced due to the following. If we write E before that hit, we can write this. Okay, this is true for x less than 0. Now we can multiply by 2m and take the square root of this, and this will give us the momentum. And the momentum, classically, we can just see this as m times b. Now let's take the other case where E is equal to p squared divided by 2m plus a b sub 0. This is the case where x is greater than 0. Okay. Now this can be seen as the following, and this is the momentum. But this is the momentum right here in this region. I will call this the region 1. This is the region 2. And I call this as the p sub 1 and p sub 2. Okay. We say that in virtue that this is greater than 0, the square root makes sense. Okay. And but we see that p1 is greater than p sub 2, and this holds classically. Okay. For instance, another thing that we will have, or we will have quantum mechanically, is this reflected component. The reflected component is not classically, it's just a quantum effect. Okay. Quantum mechanically, we have to solve this Schrödinger equation. Remember that here we have no potential due I am working with this region, with the region 1. Okay, let's specify this. And now rewrite this equation in terms of uh, the momentum. Why I say that this is the momentum? Because this is the wave number. Okay. Now let's write the wave in terms of the wave number. I multiply this by 2m and I divide this by h squared, and this is equal to 0. And this looks like wave equation. Uh, excuse me, harmonic oscillator equation, and I identify this with k1 squared. Okay, k1 squared is just 2m e divided by h bar squared, and the solution of this equation is already known. Let's call this the wave equation, the wave function 1, due I'm working with this region, and the solution is of this form. In the region 2, the Schrödinger equation changes due we have potential which is b sub 0, hence we have this term. Okay. Now in virtue of e is greater than b sub 0, if I put this e on the other side, in the left side, I will have a minus here. This is equal to 0, but I can write this, all this in this way. Okay, and this is less than 0. Okay, so we can multiply both sides by a minus sign, and rewrite this in terms of I can call this as k sub 2 squared. Okay, and the solution of this is already known. Due I am working with the region 2, I put a subindex 2 to the wave equation. So this is c k2x plus d e to the minus I k2x. Okay, I reorganize my board. Now I have two glue conditions that will help us to find these constants here. These glue conditions are the following. First of all, psi1 must be equal to psi2 at 0. This is due the probability density is a continuous function. Okay, if this is a continuous function, it cannot have a jump just right here. Another case that we must deal is that the derivative of psi1 must be equal to the derivative of psi2 at the point x equal to 0. And this condition says that the momentum must be a continuous function. Physically, this term has no relevance due I will not have a reflected component in this side in the region 2. This is due we have no other jump or other step in the potential. I just have one step in this potential just in 0, and here I must have a reflected component. The reflected component is just this. Okay, so let's erase this term, which is not physically allowed, and let's deal with the other components. Now if I apply this glue condition, okay, this glue condition just is saying that we must put here or replace the x by a 0. Okay, if I do that, I will have a plus b. This must be equal to psi 2, and if I put this x as 0, I will have c. Okay, for this side I will have the derivatives of each of these wave functions. So let's try to compute that. The first derivative must be equal to a times I k1, but I will evaluate this at 0. Okay, and this will give rise just to this equation. Okay, and this must be equal to the derivative of the other side, and the other side just is c times a k2. Okay, and this is equal to derivative of psi 2 with respect to x at x equal to 0. Now I will erase these sides of these equations, and I will also erase these i's, this I coefficient. Okay, now I can put this case on the denominator of the other side. This is k1, and we have this equation, which is very easy to solve, but I still have 3 variables here. Okay, I can add these 2 equations. If we add, I have 2 times a with c. I can factorize this c with k2 divided by k1 minus or plus 1. Thus I have a in terms of c divided by 2, and let me put it this side on this form. But in order I have a transmitted wave. What is that wave? The transmitted wave we will leave on this side, and I have an incident wave also. The incident wave is related with this coefficient a. I can write this transmitted wave in terms of this incident wave, so I have to express c in terms of a. So it's a better way. Do I also will have a reflected wave? The reflected wave is related with this b, and the b also it's better to write in terms of this a. So let me do this exercise, writing c in terms of a. So this is writing like 2 times k1 divided by k1 plus k2 times a, and after I do that, I can re-express v in terms of a. Okay, I can use this equation is very straightforward, so I put this v in terms of c minus a, but I already know what is c, so I can write this uh, put a -1 and factorize the 8 on and put it on the right. So k1 minus k1 minus k2. I can develop this fraction here, and finally we arrive to our final expression, k1 plus k2 times a. Okay, this is b expressed in terms of a. So let me organize all the calculations. I cannot specify exactly what is a or the value of a, but I see that c and b depends on a. Uh, Despite this, I can still extract some valuable information, like the transmitted coefficients or the reflected coefficients. Okay, uh, let's define what is a reflected coefficient. Is just this, r. R is in terms of the reflected current density and the incident current density. But the current density is just computed by this formula. And let me just write what is the reflected current density. The reflected current density is or must be in terms of this psi1, the reflected part of this psi1, which is this. Okay, so let me write this as psi r, and let me put an r in all these wave functions. So if I compute this current density, I will find that the following: psi r, okay, is fine. I will put the psi r just here and try to take its derivative. Okay, I already compute all the terms needed, and let's substitute all these terms here. But first you see that psi r multiplied by the conjugate of its derivative is like multiply this by this. Okay, in order, I have an exponential term with a minus sign. This exponential term cancels with this, and finally I arrive that we have b conjugate times b without its conjugate. This is modulus square. Okay, I times k1. On the other side, I have this psi r star, which I will multiply with this derivative, and finally we arrive to this expression. I have a plus sign. I have a minus here multiplied by this. Minus is plus sign, so I put all the other terms. Finally, I can put this I outside all my parentheses, which is a minus divided by 2m k1. With this 2, I will have to cancel this 2. Okay, with this 2 that arise from this sum. Okay, this is G reflected. Now I have to compute the incident current density, but it's just the same formula but I have to use here the incident index and substitute all these terms in terms of this A. Okay, if I substitute this A, I will not have a minus here. I will just have a minus here, but the I term of these derivatives will also be put down and set it here, and with this minus sign and this I, it will be a plus sign here. Okay, so I can conclude without any of these calculations that the incident current density is the same but without a minus sign divided by m. Here I have k1, the same k1. Due this is the same wave function, okay, and finally an a square, okay. So if I compute this reflected current density divided by the incident current density, see that this or note that yourself that we have absolute value, okay. Using this absolute value, I have no minus sign and this coefficient will cancel. So this is just this expression, but I already know what is A, okay. A is given by this term, so okay, excuse me, I already know what is B in terms of A, okay. So I can take its modulus square and finally just take this value and take its square, okay. This is just a square value, okay. This is the reflected coefficient. It's necessary to point out that we still don't have the transmitted coefficient. The transmitted coefficient is computed in this way: transmitted current density divided by incident current density. But we already know that the incident current what is the incident current density. We already compute that result. I have this, okay. But we still we have not computed yet the transmitted current density. It's the same calculations that I made above. So I just will tell you that this J transmitted, in order that the transmitted current will flow in the from the left to the right, I will not have a minus sign here, okay. We just will have this h bar multiplied by k2 times c square, modulus square, okay. Finally, t is just computed using this k2 divided by k1 and the ratio of these two coefficients, okay. But we already know what is c square, okay. If I substitute all these results, I will arrive to this expression, which is the transmitted coefficient. As a physical interpretation, we will find that this can be understood as a flow that goes from the left to the right. It could be a flow of particles, and these rates tell us how many particles you will find that are reflected or how many particles are transmitted, okay. You could even you can use these expressions, this transmitted coefficient and reflected coefficient, to find the number of particles that were, or the ratio of the number of particles that were transmitted forward or reflected backward, okay. It's a good use even when we study the tunneling effect. There is an experiment using the tunneling effect microscope that use this transmitted coefficient to find what the number of the or the current of these electrons that will be passed or flow between gaps. Okay, you have, for instance, consider a gap of electrons and different gaps of separated by a distance. You can model this physical situation, putting here a barrier of potential. The, later we will start this kind of potential, but you will find that you have a probability density here, and you will have a reduced probability density. Okay, but you can interpret this probability density as a current flow. Okay, from this side to the other side, and this flow will vary exponentially of the distance. To this, you can map, for instance, consider that these are not just gaps, flat gaps. Are these gaps are curved and are goes according uh, some arrangement of atoms, and you will have some atoms right here. If this varies according to the distance exponentially, you will find that the amplitude here of current find here, for instance, if you are with this needle, uh, if you move, you can find that you can maybe build a software that reads you the current flow. Okay, the current flow, and as the current flow varies exponentially, you can have a map. Okay, if you of course you have to build the software that reads that that current this variation of the current. Okay, but you can have a map, and this is the how tunneling microscope works. Okay. Okay, that's all. In the next video, I will talk about the other case where it is less than V naught. Okay, bye bye.